Okay, so let us start. So the next problem we want to solve is this one. Okay, how do you think about the problem? So I have a trigonometry involved, and x goes to pi. But when I put pi, what happens? Always make sure that you first see what happens if you put the number in. What happens? What type of limit is it? Sine of pi is also 0, so it's an infinitesimal. X minus pi, x goes to pi is also infinitesimal. So it is 0 over 0. But it is, okay, I hope that you agree that none of the methods that we learned in the first lesson is not working here, factorization, things like that. So it should be somehow related to this theorem we learned today. Yes? But then you have to engineer it some way. Okay, one thing that I want to teach you here is the substitution method. That's also good to know. For example, what I do, I want to do it once and then you will learn. So I introduce a new variable, capital X. Semicolon equals to means that I am defining it. X to be defined x minus pi. Okay? So don't resist why I'm doing this. Come with me to see why it works and then you can adjust yourself. Okay? So if this is the case, in principle, I should be able to continue this limit. If I introduce this new variable, my first goal is to rewrite the limit in terms of my new variable only. I don't want to see the track of little x anymore. So that's your strategy. If that is your strategy, I hope that you can help me. For example, what can I write for x minus pi? I want to get rid of little x, capital. So that's so far so good. But then there is a little x left there. I want to get rid of that one as well in favor of capital X. So what should I do? I would say that if capital X is this one, so what is little x then? Is capital X plus pi. Yes? Mm-hmm. So I would write sine of capital X plus pi. But then little x goes to pi. This implies, what does this imply for capital X? No. If little x goes to pi, because capital X defined to be x minus pi, capital X goes to 0. Do you agree? X goes to pi, little x goes to pi, so this means capital X goes to pi minus pi, goes to 0. So then it means that I write capital X goes to 0. It is a little bit closer to the standard theorem that we have, but we also have some obstacle here. If this pi was not there, the limit was, what we learned? 1. But what can I do with pi? The pi is there. I cannot just, yeah.
You can write it as negative.
Yes. I hope that you remember that much trigonometry from high school, that sine x plus pi is what? Is minus sine x over x. Yes? Because, for example, if this is the unit circle, let us say that if this is theta, where is theta plus pi? It means that, so you see that this is the origin. I rotate from, with the size of theta, I reach here. But theta plus pi, it means that I rotate half a circle more, and I will end up here. Okay? And then, what is the sine of angle theta? Sine of angle, so you know that there are x and y coordinates. Sine of this angle is the y coordinate. But when I go here, what are the coordinates of this one? Minus x and minus y. And then this angle is now theta plus pi. So sine theta plus pi will be the y coordinate of this point, which is minus y. So these things you need to know. If you are weak, I have put my playlist that I'm teaching extensively trigonometry. Of course, they are very long because in the high school I had a lot of time, so I was teaching very slowly and comprehensively. But you can put it fast forward and then pick up some points that you don't know. Okay? So, but this is very important. But then x goes to 0. Anyway, I am saying that this is a standard knowledge in trigonometry. And then, what is the answer to this limit now? The limit of this part, when x goes to 0, is a standard, which is 1. But there is a minus sign here. So the answer will be minus 1. Is that right?
Yes.
A very famous limit, let me do the next one as well. X sine 1 over x, x goes to infinity. Do you remember we solved something very similar yesterday? What was that? We solved this yesterday. Yes, this we solved yesterday. How many of you remember? Very bad sign. You have to remember, okay?
0.
So that's why I'm saying you have to repeat. Okay? So this was 0. Do you remember based on the theorem? Which theorem was that?
If one goes to 0 and the other is bounded.
Bounded. So this is 0. Yes? But here, even though this is bounded, this part does not go to 0. It goes to infinity. So what can I do? I cannot use that theorem. So what should I do? Again, the method of substitution. I will introduce x. Do you have any guess?
One
What
over
I'm going to do? What?
1 over x.
1 over x, very good. Yes? But let us say this part is hard, needs experience, but I have given it to you now. The rest of it you should be able to help me to do. Okay? So you might say, well, like, how should I know to do this? I don't remember when I was younger I knew or not, but I did it so many times, so I know now. Okay, now know, okay? So this is the same situation for you as well. So if x is this one, my expectation is that if I give you as a hint in the exam or in the problem, then in principle I expect you to be able to continue for yourself. So can you help me to continue? You need to know the strategy. What was the strategy? To get rid of the little x everywhere. Okay, help me. What can I write with this little x?
1 over capital.
Yes, because this means that x is 1 over capital X. Yes? So instead of this, I can write 1 over x. What can I write here?
Sine of capital.
Capital X. And now tell me, because x goes to infinity, positive infinity, this implies what?
0.
0 or what type of 0? Because this is positive infinity, so be careful that this might matter. Okay? So this is in principle x goes to 0 from the right hand side. So then it means that x goes to the right, 0 to right hand side from the right hand side. So let me make it more familiar to your eyes. So do you agree that I can write this as a fraction? Yes. And then x goes to 0 from the right. What do you know about this limit?
What?
1.
Why?
Is it 1 or not?
It is.
Yes.
Because the theorem was not the right side. The theorem was x goes to 0. But when we had one theorem, yes, if x goes to 0 is 1, the right limit and the left limit should also be both equal to 1. So I'm on the safe side, I can write.
Why from the right?
Because x goes to infinity, sometimes it matters to be so clear. Because x goes to infinity, positive infinity, and you are dividing 1 by positive infinity. Of course it is negligible, but positive negligible.
Thank you.
Is that right? Okay, and then the rest of it, unfortunately, I have to skip. And there is also a very similar theorem here. Okay, so if G is bounded, so let me record the display. If G is bounded and the limit of f of x when x goes to infinity is 0, again I use this, I can have the same theorem exactly. Okay? And I have also written that the squeezing theorem is also valid if x goes to plus infinity or infinity, minus infinity. Okay, so for example, can you tell me what is this one? I hope that you are not getting confused. They are very similar. That's why I want to solve them for you. So the next problem is the limit of sine x over x. X goes to infinity. So don't jump to the conclusion and say this is 1. Why? Because x does not go to 0. X goes to infinity. So do you see that this theorem is somehow relevant?
Yeah.
So how?
We can split that function into 1 over x
Times sine x. Very good. So this becomes the limit of 1 over x sine x. X goes to infinity. Do you agree? But then this is bounded. This goes to 0. So according to this theorem, the answer is 0. Yes? Yeah, please do the other ones yourself. They're a little bit more tricky, but they are simple. Yeah, it's very strange. Okay, so the next one. Let us go to display here. This is very important, and that is the notion of continuity. Let me talk a little bit about that. You have an intuitive idea of what continuity means in real life, okay? But in mathematics, I say that a function is continuous if the graph of the function can be drawn with one pen stroke. Yeah, that's an intuitive definition, of course. So it means that, for example, is sine x a continuous function? Yes, if you have seen something like this will happen, yes, for the sine function. So I can draw it in principle by one pen stroke, but is this function continuous? No, because if I can draw this part with one pen stroke, but then I have to lift my pen and put it somewhere else and then continue. So that's not one pen stroke, yes? So this is not continuous. Okay, but the logic is different. If I give you the graph of a function, even a primary school kid can see which one is continuous, which one is not. The logic is the other way around. I don't have access to the graph of the function. Instead, I have access to the formula of the function. For example, I know that f of x is equal to, I don't know, for example, x squared plus sine x divided by cosine x. That's a formula. I don't even know how the graph looks like. But the point is that I want to anticipate something about the graph of the function. I want to see that if I can draw the graph of the function, is it a one-piece graph or it will be different pieces? So it means that I need a mathematical definition so that I can check it analytically to predict something about the continuity of the graph of my function. Is that right? So this is the logic you have. And mathematicians actually came up with the definition that a function is continuous at a point if the limit of f of x, x goes to a. A function f is continuous at point a if this holds. It means that when I calculate the limit of the function when x goes to that, it exists and it is also equal to the value of the function at that point. For example, you see that if this is a and this is like this, the whole graph is the function of f. So you can see that the function is not continuous at a. This is clear. But let me show you that this will also does not satisfy the definition. Why not? Can you see that? If I approach to a from the left-hand side, you see these heights are increasing. They will stabilize themselves around the point, let me call it L. So this means that in this picture, intuitively speaking, the limit of f of x when x approaches a from the left-hand side is this number L. Yes? But now let me approach a, but from the right-hand side. So let us say that I am here and get closer and get closer and get closer. Every time this length is shortening, but it will stabilize around which point? M. So this means that the limit of f of x when x goes to a from the right is m. And you see that they are not equal. So it means that the limit does not exist. Is that clear? So this means that this is a very good definition, because when I checked it, I see that it is not satisfying this and it was not continuous. So it's a good definition. Or for example, what about this scenario? And if this point is A. Is this continuous? Of course not. I cannot draw it with one pen stroke. I should come to here, pick my pen here, and then come back here. So it's not continuous. What do you think? Do you think that this definition shows me that this is not continuous? In this case, the limit of f of x when x goes to a exists. Yes? For example, if I approach a from the left, it will stabilize itself around the point L. And if I approach to a from the right, do you agree both of them are L? So this limit really exists. But what is f of a? F of a is m. So the limit exists and it is equal to L, but the value of the function at that point is a different number. So again, this equality does not hold. So it's a very good definition. So it highlights that this is not continuous. So anyway, this is the definition of continuity of a function at one single point A. But if I say that a sine is continuous, It means that no matter which point you choose, the function is continuous at every single point. So when I say that I have a continuous function, I mean it is continuous at every point in its domain. Otherwise, I have to specify which point I am talking about. So for example, this function is continuous everywhere on the left of A. It's continuous everywhere on the right of A. But there is one discontinuity for this function, and that is exactly x equals to A. Is that clear? Okay. So let me solve one example at least. So this I want to solve. Determine k such that the function f defined by this rule be continuous. I think I should write is continuous. Okay, is continuous at x equals to 2. So f of x is equal to kx squared when x is less than or equal to 2, yes? And the other one is 2x plus k if x is greater than 2. Okay, the point is that we want to adjust this k so that this function becomes continuous, yes? So I want to find k so that, so you know that, for example, if I just randomly choose k, I don't know what the number is, but let me choose k equals to 1. Then I draw the graph of this function. It's a parabola, but I will accept it on the left-hand side of 2. I put 1 here, it becomes 2x plus 1. It is a line, but I will accept it the right-hand side. It might be the case that they are not glued together. Okay? So it means that I want to fine-tune the k so that this piece glues itself to that piece, so that it becomes one piece. Is that right? Okay. So this is the meaning. It's good to understand the meaning. But how should I solve it? It's extremely simple. I have to follow the definition. I want the function, I want to force the function to be continuous at 2. So this means that demand is what? My demand is limit of f of x, x goes to 2, should be f of 2. Yes, this is the demand that I put on this because of the problem. Okay, f of 2 is very simple. You'll help me. What is f of 2?
Okay.
I send 2 in. Which part accepts 2? The top one. So the top one accepts 2. It means that I will replace this x with 2. So it becomes 4k. Yes? Okay. But can I calculate the limit directly, the both side limit? No, because it depends in which direction I am approaching. So it means that even though I want this limit, based on the experience we got yesterday, I myself should understand that I have divided the problem into 2 problems, yes? So tell me, what should I do here? X goes to 2 on the right hand side. Which rule I have to use? This one. So this becomes the limit of 2x plus k, x goes to 2 plus. Then becomes 4 plus k. And this one, x is less than 2, so I use this one. But you know the answer is 4k. So this number, and this number should all be equal. 2 of them are automatically equal. So this means my demand tells me that this should be equal to that. Then it means that k is 4 over 3. So you see that I just picked randomly 1. So if you do it from an application, draw the graph with 1, you see that they are not one piece. But exactly this is the number that I have to choose so that these 2 parts glue together. Yes?
Regarding the definition of a continuous continuity at a point, is what if we say a is infinity because functions are defined for, some functions are defined for infinitely large?
No, we cannot talk about the function continuity at the point x equals to infinity. Infinity is just a behavior. When I say x goes to infinity, I am just conveying the message that x is extremely large, larger than any positive number that you can imagine.
But we can't say that for any very, very large number this function is continuous.
No, just very, very large is not good enough. You just need to tell me which number is that.
Okay.
Then I can talk. Or I can say that, okay, I prove that this function is continuous at any large number a according to this argument. Then you can choose a whatever you like. This is the logic. Yes? Yes, please.
So infinity is never part of the domain of the function.
Yes, that is also, I am following the textbook. The textbook talks like this. For example, the textbook, if you draw the graph of the function 1 over x, if I ask you, is this function continuous or not, the book consider this continuous. Yes? So that's why I took that definition, because they told me that the course book is this one, so I don't want to confuse you. You say that, okay, at any point on its domain, because when I take the function 1 over x equals to 0 itself is not in the domain. Yes? So it means that if you want, but I saw the workshop problems, if I ask you, is this function continuous at x equals to 0, in this course you should say no, it is not continuous because it is not even defined. Yes? But that is a different. Again, the course book is also not telling you that this is continuous at 0. But it is telling you that this function is considered to be continuous because it is continuous at every single point of its domain. Is that clear? Yeah. Yeah. Yes, I could explain more, but unfortunately, this is more, it is not teaching, it is like a gym practice, yes? So I'm just running, okay? By the way, I know this is not very common, but it was common for me when I was teaching master level courses. Are you okay to be here during the lunchtime or not?
Yeah.
I mean, you can eat, I can teach. This is the way, because I'm not forcing you, but I mean, learning, it depends how determined you are to learn, okay? You see that I am doing my best. I don't think you could learn everything on your own. Yes, that's what I'm saying. And I know I can, of course, solve 2 examples, 1 example, and just skip everything. This is not the good way of learning. So I am ready to sacrifice. I'm not going to be paid more. So if you are also ready to sacrifice for yourself, we can have an agreement. Sometimes we can work more. That's I just told you. And if I have a volunteer to join when I am recording videos, yeah, please send me a message. I can record on my own, but then I have to pretend I'm talking to people. I prefer to really talk to people, okay? So if you're a volunteer, have a teamwork so that I can solve some of these problems, make videos and publish. If not, I have to come here and find, I can pretend that I'm talking to people. Okay. Let me solve one exam problem. This is a good one. This exam problem, so let me first show it on the display so people can see. Let us read the question. Exam question 2020. Assume that the function f of x is defined on the whole real line and this inequality holds. I don't know anything about the function except that this holds this. Determine whether f has to be continuous at x equals to 0 or not. Okay? Justify your answer by providing a proof, if you believe this is true, or a counterexample. It means that bring an example that shows that this is not correct. So, yeah. And of course, this is only one part of the problem. There were some other parts, but you couldn't solve those parts yet. Okay, so you see, that's what I'm saying. If you don't understand how to think, which question is that? Question number 6. Of course, question number 6 means that this is in more advanced part. Okay? So if you want to solve this, what I know is that the function f of x is defined everywhere, so I don't have any problems which numbers that I want to put in. But I know that this is this one, x to the power of 6. And my question is that, do you believe that this function is continuous at 0 or not? So the question is asking you, is the limit of f of x goes to 0, is equal to f of 0? This is something they are asking. I mean, if I see the question, I go to a scratch paper, I think around these lines. Okay? And I try to use my experience, my toolbox, yes, and my memory to see that what I can do with this one. Okay. First of all, let me start with simple ideas. Okay, if I want to answer this question positive, this question is a little bit not fair because first you have to decide to prove or to bring a counterexample. These are the hardest ones in mathematics. Okay. But let me just give you, because we don't have time, we want to prove it. If you want to prove it, I want to calculate this, and show you that they have to be equal. But let me make it simple. Do you have any idea for me, how can I decide the value of f of 0 based on an inequality? I don't know anything about f, I know that this is working here. But I want the exact value of f of 0. Yes?
The right hand side is equal to 0 and the left hand side is less or equal than that. And it's squared, so it can't be negative. So the only possibility is that it's equal to 0.
Yes, so it's, yeah, very good. So what you are telling you, the problem tells you that this is valid for every x. If it is valid for every x, it is also valid for x equals to 0. So this means that if x is equal to 0, this means that this is f of 0 to power 2 less than or equal to 0 to power 4 plus 0 to power 6. But this means that f of 0 to power 2 is less than or equal to 0. This is according to what problem tells me. It is valid for every x, including one x that is 0. But why did I choose 0? It was not very hard to guess, because I want to talk about f of 0. Why should I put 1 there? Yeah, so it's not hard. But how can I conclude? On the other hand, I know something. I know this number is less than or equal to 0, according to what problem tells, but I have some knowledge myself. I know because of this even power, it should also be greater than or equal to 0.
Yes.
So I have a number, which I don't know yet, but I know this number is sandwiched between 0 and 0. There's only one possibility. So this means f of 0 to power 2 is 0. But if f of 0 to power 2 is 0, so this means f of 0 is also 0. Yes? Okay. This is the first thing. But what about the limit then? I want to test your understanding. Which part of the course you will actually think about to find the limit?
Squeezing through.
Yeah, something like that. Why? Because I don't know f. I have inequality for f. So if you look into your toolbox, there is only a squeezing theorem related to this. So a squeezing theorem, I want to have f of x. For example, I will take a square root. For example, if I take a square root, by the way, do I have problems taking a square root on the right hand side? No, because x to 4 is positive, non-negative, non-negative. So I don't have problems with that, yes? But do you remember what I told you about this? What should I write for this one? Absolute value is less than or equal to this. Okay? And then what can I write? I can write that f of x is less than square root of x to the power of 4 plus x to the power of 6. Can you complete it for me? If I want to lift this, if I want to take this off.
It's greater than or
Greater than or negative of that. Do you remember? The distance to the origin should be less than this one. So it would be between minus that number and positive that. Okay? But now, let me ask you, of course in exam you have to write more properly, but x goes to 0. What is the limit here?
0.
Is 0. What is the limit here?
0.
Also 0.
So a sandwich theory.
It's sandwiched between 0 and 0. So what is the limit of the sandwich one?
0.
It's 0. So the limit is 0, the value of the function is 0, so they are equal. So the function is continuous at 0. Is that right?
Yeah.
Okay. Okay, so let me continue. For the time being, let me skip these ones. You can read it a little bit yourself. So let me start these two leftovers that are essential, and if we have time we come back together. So there are two theorems that are very important. One of them is max-min theorem and the other one is the intermediate value theorem. Okay, so let us understand what is the content of the max-min theorem. So let me read it first for you. Let f be a function that is continuous, so that is one important word in this theorem, on the closed, and that is the second important word here, and the closed and finite. Three important words, yes. Yeah, because usually the unbounded ones cannot be closed, okay? Anyway, is continuous on the closed and finite interval from A to B. Yes? Then F has the absolute minimum and the absolute maximum on A and B. In other words, there exist numbers C and D in A and B such that for all x in A and B, we have this inequality. Okay? This is much simpler than it sounds. Let me explain it here for you. Okay, so this means that if you give me a function that is continuous on a closed bounded interval, so it means that, for example, let me choose this point A, this point B, and let me draw a solid line here and a solid line there. What happens for my function outside this strip? I don't concern about that, but let me say that I have a function which is continuous and it is in this closed interval. For example, let me start from here. I want to go with one penny stroke somewhere. For example, I go up here and then I go down here and then I go here, for example. So this theorem tells you that no matter how you draw this continuous curve, very simple, there is a highest point and there is a lowest point. Is that clear? Okay. For example, here, this is my highest point. For example, it occurs, let us say, at C. And here is my lowest point. It occurs at D. Yes? Do you agree with me that any x that I choose here and calculate my f of x at that point, it's always greater than f of D and it is always less than f of C? Yeah. Do you agree? Okay. So what is the importance of this theorem? So let me test your understanding about this. If I draw a picture like this, let me fill this up, momentarily forget about this picture, and I draw this one. So by this I mean this point is included, by this I mean that one single point is carved out and excluded. Now my question is that, let me give you this is A, let me give you this is B, let me give you this height is L, let me give you this height is M. My question is that, and this is the function f, and so this interval is also, so this interval is not closed, you see this. Okay, so now what I'm saying is that if I ask you what is the maximum of f, and what is, let me talk about minimum first. What is the minimum of f? What is the minimum of f in this picture? It means the lowest value of f.
A.
No, A is the point the minimum is attained. Okay, the minimum is the value. So the lowest value is it means the lowest height. The lowest height is L, but is attained or is assumed at x equals to A. So in principle, A is minimizer, L is the minimum. Is that correct?
Okay.
Okay. But now let us talk about maximum. The same picture. What's the maximum?
It doesn't show exactly. It's a limit.
So what do you say? If I ask you what is the maximum?
It approaches
Yes.
So what is the final word?
the limit.
So your intuition is correct. What is the maximum?
M is the limit.
And
Any other intuition? The question is simple. What is the maximum? There should be one answer. Your intuition is completely correct. You understand there is something wrong there. But I hope that you understand the answer to this question. What is the maximum? The answer is the maximum does not exist.
Okay.
It's very important, yes? Why it doesn't exist? For example, let me just describe it intuitively. Is this point the maximum?
No.
No. Why is that? Because I can go higher. Is this point now the maximum?
No.
No, because I can go higher.
There's no.
Is the next point
the
the highest point? No, because still I can go higher. So there is no maximum because there is no end to the number of approaches that I can make.
Just an approach.
I can go higher and higher and higher, but I don't reach to the highest. Is that clear? So this means there is no maximum. Okay? So, do you think this is falsifying this theorem? No, because was the interval closed? No, it was not closed. So that is why continuity and closedness are essential to this theorem. If you relax one of these conditions from the theorem, might be the result is no longer valid. Is that correct?
Yes.
Is that understandable? So, at least in this example, you see that if the interval is not closed, there is no guarantee that there is a maximum or there is a minimum. Of course, here the maximum does not exist, but the minimum still exists. I can draw another picture. For example, I can hollow this one as well, so there will be no minimum. Okay? But why continuity matters? Can you see why continuity matters? If I keep the interval closed, but I relax the continuity condition,
Then we know the value of every point, so we can assure which one is the
so
maximum.
can you draw a picture intuitively, make it clear for everyone? What I am telling you is that let me keep the condition of closed interval, but let us now relax the condition, the assumption of continuity. Can you draw a picture to show that, okay, in that case might be there is no maximum or there is no minimum or both? Yes.
Yeah, because you could have bits of the lines are way up, or you don't know where they are. They're not.
So help me to draw it.
Yeah.
So for example, I go here, yes, for example, I go up there, and then I make it hollow, and then I jump here, for example, yes, and then I go like this. For example, if I ask you what is the maximum of this function, doesn't exist. Because of the same reason, there is no highest point. But is the interval closed? Yes. But is there a maximum? No. So what is the problem here? I have relaxed the continuity. So I want you to have an intuitive understanding of this theorem. Proving this theorem is extremely hard. So you need a little bit more. Even though it's very trivial, these trivial ones are very hard in analysis. So you need more tools. Okay, but intuitively it is very simple. Is that clear? Okay. So from now on, if a function is continuous on a closed interval, it is guaranteed that there is a highest point and there is a lowest point. One question, do you think the highest point is unique? Can I jump into the conclusion and say that the highest point occurs at a unique point?
No.
No. It's like sine function.
It could be a line.
Yeah, it could be a line. So the max and mean is everywhere. Yeah, is that clear? Okay. So for example, let us check this theorem, this problem from the modules. So explain. This is a mod. I think it's in your workshop problem. Explain how you can be sure that this function has a maximum and a minimum value on the interval. What type of interval is this? 0 and 3, including closed. Okay. So what do you think? Do you think there is a max and there is a min for this particular function here?
As long as it's...
Yeah, but you need, because you know, I skip some parts, you read it yourself because that's very simple. There is a theorem that if I have two continuous functions, the subtraction, the addition, the multiplication are all continuous. So for example, sine 47x is a continuous function. It's a sine function. And cosine x to power 3 is also a continuous function. So this is the way you have to write in the exam. So I say that this function and that function are continuous, and the difference between them, according to the theorem I skipped, is also continuous. So the numerator is continuous. The denominator is also a polynomial. A polynomial is always continuous. This is also a thing guaranteed. But when I want to divide, the only thing that I have to be worried about is that if the denominator is 0 or not. Is it? It might be 0, but I am working on this interval. On this interval, I hope that you agree this is not 0, because the minimum value is 0 and all the terms are positive. So the minimum value of the denominator is 1, so it cannot reach to 0. So I'm on the safe side. The numerator is continuous, the denominator is continuous and not equal to 0 for any value in the interval. So what does it mean? It means that the whole package of the function is continuous and the interval is closed. You write like this and then say, according to max-min theorem, this is continuous. Sorry, according to max-min theorem, it attains its maximum and minimum. Okay?
Question, if we did not have the +1, then how would we explain,
No, in that case, it might be true or might be false. By the way, I am not saying that if you relax those conditions, it is guaranteed that there is no max or min. But I'm saying that if you have both, it is guaranteed to have max and min. Yes? So if you take that one off, I can see that there is no max. Because if you take that one off, can you see why? Because if you take that one off, then what happens when x goes to 0 from the right hand side? Can you guess what happens?
goes to 0?
The denominator goes to 0, the numerator goes to a number, so the whole function blows up. So it is not bounded. If it is not bounded, there is no maximum. For example, yes? But these are not easy questions. I mean, these are easy questions to design, but it is not that easy to answer. So usually they will ask you about the questions that you can solve at this level. Okay, so let me start the next one. This is a little bit more interesting theorem, but again, the proof is hard. But the idea is very, very trivial. So first of all, let me read it for you. The intermediate value theorem. Let f be a function that is continuous on the interval, closed interval a and b. If r is a number strictly between f of a and f of b, then there exists a number c in the open interval a and b such that f of c is equal to r. Okay, so again, it might seem hard, but it's extremely simple. Intuitively, proving it is hard. So the proof of these theorems are not mentioned in the text, they are mentioned in the appendix. And this is not a standard. This is a standard problem in mathematical analysis, not calculus. Okay, so could you understand what this theorem is telling you? It tells you that let me have a function, let me have a closed interval, but I know that this function is continuous on this interval. Okay? So this means that I can calculate f of a, I can calculate f of b, and they are two numbers. One of them is bigger than the other one, or might be they are both equal. Sorry, they have to be not equal. One of them is smaller than the other one. And let me say that r is between f of a and f of b. Okay, r is just a number that I pick between f of. For concreteness, for definiteness of discussion, without loss of generality, if you don't mind, let me assume that f of a is less than f of b. It doesn't matter. Everything I say, you can say for the other way. Okay, so let me give you a picture. So let me have this interval from a to b, and then I have f of a is here, for example. This is my f of a, and this is, I assume that f of b is higher, so let us assume that here is f of b. Okay, and now my function starts from this point, goes to this continuously, in any manner that you like. Let me draw one of them, for example. So, yeah, let me just go like this. Okay? A very simple continuous function from that point on. Now, let me pick a point between f of a and f of b. For example, let me pick this point here, r. What this theorem claiming is that there is a point on the open interval, not this one, not that one, that will map here by the function. But that is very clear where that point is. You see, if I want to find the point which is mapped to this r by this function, I reverse engineer that. So I cheat a little bit, and this is points. So do you agree there is a c? And if I ask you what is f of c, what is your answer? R. Do you agree that if I change r from here to here, there is another one? For example, which one is that? The capital.
C plus.
Yeah, so f of c. But the point is that you cannot escape this destiny. What number you choose here there will be at least one number here which is mapped to that number. Why I say at least? Because hopefully you see that this is not the whole story. Sometimes there might be more than one. What is that? For example, if I clean this, and let me just do this. Yes, this is my function. And let me choose R here. Okay, here how many numbers you can see that is mapped to R? Reverse engineering that. Yeah, here I have one, here I have another one, here I have another one. But it means that you cannot escape this. Yes, there is at least one which is mapped to your number. Is that clear? But that's the content of the intermediate value theorem. So one very interesting problem is that you can prove that at any instant of time there will be 2 points on the planet Earth which are opposite according to the equator, having the same temperatures. That's a very nice, I mean, this is a very simple idea, but it gives rise to the problems, non-trivial problems like this. But let me explain one more thing. There is one version of it we might need more, and the version is that these numbers are opposite in sign. It means one of them is above the x-axis, one of them is below, and I choose R to be 0, because R should be chosen between f of A and f of B. Let us imagine a case that, for example, f of A is negative, if this is A, f of A is here, and choose let us say that f of B is positive. Okay, and then you want to go from this point to that point continuously. You have to cross, you have to intersect the x-axis. There is no way out of it. Yes? If I want to go from here in a continuous way to this point, it is inevitable. I have to cut the x-axis at least at one point. I might cut it in more than one point. Do you see that this is the intermediate value theorem?
Yeah.
So f of A, I have shifted it a little bit downward. So what is R in this problem?
0.
0. R is here. This is valid for every R between these two numbers. But if these numbers are one positive, the other one negative, or the other way around, I can choose R to be 0. Of course, I can choose R to be here again, but one particular case that is important for us is R equal to 0. So what does it mean? It means that if I multiply f of A by f of B, and it turns out to be negative, what is the meaning of this? It means one of them is positive, one of them is negative. So it means that either I have this situation, or I have the other way around situation. But in any way, it guarantees that the function, the equation f of x equals to 0 has at least one solution in the interval between A and B. This version of the intermediate value theorem is the best one. Yes? So if I have a function which is continuous on a closed interval A and B, and when I calculate f of A and f of B, they have different signs, meaning that when I multiply them it becomes negative, then it is guaranteed. If my goal is to guarantee the existence of a 0 of this function, I have it. Intermediate value theorem guarantees that. Is that clear or not?
Yes.
Are you with me? Or you are starving? Are you okay?
Yes.
Okay. So, for example, this remark is also important, the moreover one. Read it yourself, okay? Let us solve the example 20. This is a very simple, standard problem using this. Show that the function p of x equals to this, as you see, has a real root in the interval from -1 and 2. So, the type of the questions I hope that you're getting familiar with. So let me write this here. So p of x is what? Is 2x cubed minus 5x squared minus 10x plus 5. And the interval is given to be is -1 and 2. Okay?
R could be 0.
Yes, so we want to show that there is one 0 at least, because you know that this is the third degree. Usually the third degrees might have up to 3 roots. But guarantees that one of the roots at least is inside here. Okay? Okay, so how should I solve the problem? I consider the function p of x. I consider the interval, closed interval from -1 and 2. Yes? Yes. Okay. And now I calculate p of -1, the endpoint, and I calculate p of 2. Okay? So p of -1 is clear. I put -1 here, so it becomes -2, -5, plus 10, plus 5, so it becomes 8. And I put 2 there, so this becomes 16, -20, -20, plus 5. So it becomes what? -24, 21 minus 24, no, 40, and 21 is -19. Am I right?
Yes.
Yes. And then p -1 times p2 is positive or negative?
Negative.
Negative. Okay? So it is exactly a very standard problem. So therefore, you need to write in the exam according. Okay, one more thing. One more thing you should also mention in exam. What type of function p of x is? Continuous. Because if it is not continuous, it's not valid, you know. I can go from here to here, I can come up to here, then I put my pen here and continue. And I do not have any zero. So continuity is extremely important. So in the exam, you should say that p is a continuous function on this interval, and then I calculate this. So according to intermediate value theorem, for example, what can I say? I can say there exists, this symbol means there exists, or you can write it in word, there exists what? A C, where in the open interval, such that P of C is equal to 0. Do you agree that we are done? Because I wanted to show you that there is a number here that makes P 0. But be careful, this is an existential theorem. Do I know something about C? No. I know C is here. What is that C? I don't know. But it gives rise to an approximation method for finding that solution. It's called bisection method, and it's explained a little bit in the book as well. Okay? But this is a very standard problem. Okay, let me immediately go to the next one. That's a model question. But one question. Let us say that I multiply them and turns out positive. Okay? It might be the case. If it turns out to be positive, what can I say? Can I jump and draw the conclusion, oh, there is no root there? No. Be careful. If it works, it is guaranteed. But it doesn't mean that if it turns out to be positive, I can conclude that there are no roots. It might be there is still some roots there. You see why? For example, I can have this scenario, and I can have this scenario. So f of a is here, f of b is here. Okay, so if I say f of a, f of b, is it positive or negative in this picture? Both of them are positive, so it is positive. But it might be the function is like that. So and then I have actually two roots there. So if you are unlucky and this turns out to be positive, you have to make the interval shorter so that somehow it works. Is that clear? For example, let me solve this problem and then we are done. I think we are right in time, but anyway. So the next question is what? F of x, I want to show that x to power 4 minus x to power 2 minus 2x minus 1 is equal to 0 has at least two different solutions in the interval from -1 and up to 2. Okay? So we want to show that this equation has at least two distinct solutions in this interval. Yes?
So you just have to show that it's continuous.
No, you have to write all of them. For example, if in the exam you have to say that let p of x be equal to this function, okay, and mention that p is continuous because it's a polynomial function. A polynomial function is continuous everywhere, including the, so you need to write these things. Let p of x be this. P of x is a polynomial function, so it is continuous everywhere, including the interval from -1 and 2. Okay, so that's the starting point of the exam writing. And then, what do you do? Because I need two solutions, so one interval is not good enough for me, because one interval at most can guarantee how many roots? One root. Okay? So it means that I have to somehow do the same process for two intervals within this. And then there is no obvious way how I should split it. But my advice is to take the most natural one. If you want to split this interval into two pieces, what is the most natural number comes to mind to split?
Negative 1, 0.
Negative 1, 0, and 0. If it works, you are done. If it doesn't work, you have to do some trial and error. Yes? So, it means that I divide this interval between this and that, and this between 0 and 2. Okay? And, because there is no time, I have to stop. Do the same problem, where was it? Up there. For this function and this interval, you will see that there will be one root. If p of -1 times p of 0 will be negative. I have done it at home before. So it will give you one solution. That solution is where? Is between -1 and 0. And do the same process for this. This will give you another one, where between 0 and 2. So you were able to guarantee that this function, this equation, has one root here and one root there. Can these two roots be the same? No, because one of them is here, between -1 and 0, the other one is between 0 and 2. So these roots are this thing, and you found 2. So it means you found at least 2 distinct roots of the function. Is that clear?
Yes.
Okay. Unfortunately, there are much more. Theoretically, more or less, we covered everything, but there are some a little bit harder problems you can see, and I gave you some hints. For example, this one in the exam, is a little bit harder than the one I gave, but it's good to think about them, and if you have problems, of course, you can do it on the workshops. And as I told you, my goal is to make videos about these leftovers and upload them, so in case.
If you want to keep going, I want to stay.
Yeah, so how many of you want to stay, and how many of you want to leave? No, okay, so that is a little bit tricky, okay? Because if I ask, people might be trying to say that we want to stay. But how many? So let me stop recording.